Hi, in the previous video, I showed how Keras could be used to train a convolutional neural network to detect digits from 0 to 9. And in this video, I'm going to use also Keras with a similar convolutional neural network to train the neural network to be able to detect cats and dogs in images. Okay, the first step is to load the images. So we're gonna use this Kaggle website, which has a bunch of cats and dogs images. We can download it from here. This is the link. So you have to create an account that is free, and once you download it, you're gonna get something like this, which is 25,000 files. So cats and dogs both are in the same directory. So the first step is that we're gonna create we're gonna rearrange these files to so that to enable the integration with Keras. So we're gonna create a cats and dogs small. We're gonna resize them, I think, and we're gonna create three directories. So we're gonna split the data for training, validation, and testing. Training is what is going to affect the weights of the neural networks. Validation is going to, well, for each epoch, we're going to test it against the validation to see how off and how general is the training. And finally, the test is going to be used to, once the epochs are finishing the training, we're going to use the test to see how accurate our neural network is. So within each of these folders, there are going to be a couple of folders, one for cats and one for dogs. And yeah, so basically, this is so that Keras can infer the labels for the images. So all the images under dogs here are going to have the label of dog, and all the images under here are going to have the label of cats. Notice that this problem is going to be a binary problem, a binary classification problem. So the output is going to be 0 or 1. Okay, so this is the folder where the original images are. So we're going to use this operating system utility to concatenate the folder, the original training, original test. This is the new folder. We're going to use the operation system utility to create the folder. Then we're gonna create a training, validation, and test of folders, create the folders, and within each of them we're gonna create cats and dog subfolder again using concatenation and making directory. And yeah, and that's gonna be for validation, training, and test. Finally, we're gonna copy 1000 images of the original folder from the original folder to the cats folder, 1000. And 1000 also for here for dogs, 1000 for dogs from the original to the training dogs, and then 500 for cats, and 500 for dogs for the validation, and 500 for cats for test, and 500 for dogs. So here, once we do this copy using this sh utility, which basically copies a source file from destination, so we just get the file names. Yeah, we get the file names from where we get them, from fnames. Yeah, basically we know the names already, so we use a range in here and format it to get the name of the file, and then with that we concatenate and just copy using sh util from the source to destination. Okay, so once we finish the copy, we are gonna use this list here to count the number of files within the new folder for training, validation, and test for cats and dogs. So we have 1000 cats, 1000 training dogs, so we have a total of 2000 training samples, and 1000 validation samples, and 1000 test samples. Okay. Yeah, I don't run this again because the folders are already created. Okay, so now let's go to do the actual code. And again, this training this neural network is takes a lot of time, so I'm not going to run it again. I'm going to just show the results. Okay, so we take the base directory of the new folder cats and dogs small. I think the images were resized. No, they were not resized. Yeah, I guess by small means the small amount of samples, because think about it, we only have we have 25,000 images, so we only copied a total of 4,000 images, and maybe this is on purpose. This is on purpose to train this neural network on a small set. That's what we want to do, because in reality, it is hard for a regular problem getting 25,000 images. So we just on purpose want to train this with a small amount of samples. So that what is the small missing here. Okay, so we're gonna get the folders for the training, validation, and testing, and we're gonna create the convolutional neural network here. So we also use convolution like the previous example. We use 4 pairs of convolution and max pooling. Convolution is for the local feature, max pooling is for the features between features, that is to find global patterns. So you're gonna use a 3x3 window for convolution, 2x2 window for max pooling. The rectified linear unit is going to be the output of each layer except the last one, and this is for your regularization. The input is going to be 150 image, so is this a larger image than in the previous digit example? And now instead of grayscale, it's going to be red, green, blue, 3 colors. Okay, so the output is going to be first 32 channels, and as we go forward, we're going to increase the number of features. And finally, after all the image processing is done by the convolutional neural networks, we're going to flatten to get the result. And then we use a dense layer for the final classification of cats and dogs for with 512 features, again, a rectified linear unit. And then finally, we put another dense layer to get the output. And the output is going to be only one, because we only want to detect if it is a cat or a dog. And we choose a sigmoid for the output. And there's some suggestion. For binary classification like this one, cats and dogs, it is suggested to use sigmoid. And for the training, binary cross entropy. For the last problem, we classified digits, which are 10 possible outputs. So that is considered multiclass. So for that example, we use softmax, and we use categorical cross entropy. And here are other types of problems and some suggestions for the final layer. Okay, so now we create the model and get the summary of it, and we can see again we are not using padding, so we for each convolution we're going to use lose the borders. This is the output is the number of features. Max pooling is gonna divide it by half and then lose the borders again. Divide by half, lose the borders, augment the features, and eventually you get a very small image. At the end of this, this image should look close to the input image, but at this point it's almost unrecognizable. So then we flatten it and get a bunch of features. We get 512, and then finally we get 1 with the output. Okay, now we're going to compile the model, and for that we're going to use binary cross entropy for the loss function, root mean square propagation for the algorithm of training the neural network, and acceleration as the metric. Okay, now to load the images, we're going to use this utility, image data generator. For the first try, it's only going to help us in do some pre-processing and also to load the images, but also it's very useful for data augmentation, which I'm going to talk next. Data augmentation, for example, in here we only have 2,000 samples for training. But with data augmentation, we can multiply that into 10,000 or something like that. We're going to show later how to do it. Okay, for now, we're not using data augmentation, so we're rescaling the values because neural networks work better with values between 0 and 1, and the values of the image are from 0 and 255. So we're going to rescale them, get the generator, but the generator at this point do not have the images. You have to call the flow from directory to load the images and specify the size. So there's going to be a resizing in the image, and also 20. There's going to be 20 samples per batch. So that's going to be part of the tensor, the first dimension of the tensor. and the classification mode is binary, so it's going to be 0 or 1. And there's a class parameter that, if not specified, is going to this image data generator is going to assume that the labels are determined by the subdirectories. As shown earlier, these are the cats are within this folder, so we specify in the train directory, we specify in this directory, so it's going to infer the labels automatically from this. Okay, so we get the default, the train generator with the images, and the validation is going to be similar. We have binary classification, same batch size. So now we're going to take the first one. This iterate basically by iterating and breaking in the first one, we're going to break in the first to just get the first one, just to see how the data we're gonna get the first batch, data batch, and label batch, and to see just the shape of them. Okay, so the first one, as expected, you have an image 150 by 150 with 3 colors, but you also have the first dimension is the number of samples. Now we have a tensor, a batch tensor. And also the output is going to be 0, 1, it's only one scalar. It will be a scalar, but since we have 20 samples in the batch, then it's going to be a vector of 20. Okay, now we're going to train the neural network. We're going to give the train generator, which is the generator, image data generator with the data, training data, and the validation generator, which is the other generator with the validation data. Okay, we're going to train it for 30 epochs. This is the number of times all the data is run through the neural network to train it. And you can see the epochs in here, 30 epochs. Okay, then the steps per epoch is determined as follows. We have 2000 training samples. So you divide that by the batch size. By divide by 20 is 100. So you need 100 steps per epoch. And we have 1000 validation samples. So you divide that by the batch sample size, which is 20. That would be 50. And that is what you're using here. Okay, so this is going to take maybe 10 minutes. For this case, it could take more, maybe 20. So once it finishes training, at the beginning it starts with 55% of accuracy. So that's as good as flipping a coin to tell you if the image is a cat or a dog. So that's going to improve, and the loss is high also at the beginning. So you're going to get a history object as a result with all the data. So that's going to increase, it's going to increase, and it's going to increase all the way to 98%. But the validation is not doing as well. You can see that the validation increases, accuracy validation increases up to some point and then stops, is stalls in there. Okay, so now that we train the model, we're going to save it so that we don't have to train again. This is a costly operation we don't want to do twice. So once you save it in the NumPy, in the Jupyter notebook, you're going to get the file in here. Okay. So now we're going to use PyPlot. Using the history object, we get the array of the history of accuracy, validation accuracy, loss, and validation loss. We get a range from 1 to the number of accuracy objects, and this is the same as the number of epochs. That's going to be our x values, and our y values are going to be the accuracy or validation accuracy. We put a title and the legend and just put another figure and show everything. Okay, so we get this. You can see that the training goes all the way and makes it very accurate, almost 100% for the training data, but that's very bad overfitting. The validation stalls in here at 70 something percent, which is bad. Maybe I think it was 73%. And the loss, again, the loss goes down, but then start to get worse and worse and worse for validation, but it's perfect for training data. So we have a horrible overfitting in here. Okay, so what we're gonna do to remedy the overfitting, we're gonna do data augmentation using the image data generator object, and also we are gonna use dropouts. We're gonna talk about both in a moment. Okay, for the image generator, in addition to the pre-processing, let's try first with a single image. You have some options to do a rotation. You specify the rotation range. You specify how much you're gonna shift it. I think it's translation. How much you're gonna shear it. If you're gonna flip the image horizontal or not. So basically, this is gonna do a bunch of affine transformations to supply a bunch of variations of the same image, so you don't see the same image twice. So this is kind of random. And that way 2000 sample image will become 10,000 or more. And for example, also you have to specify how you're going to fill the blank pixels. For example, if you rotate an image, there's going to be some pixels that are going to be left blank. So instead of leaving them blank, then you're going to use the nearest pixel to fill that pixel. So we get the image data generator that is augmented. So now we're going to just take one file from the list of files in the training cats folder. We're gonna get all the file names, and we're gonna join the file name in here to get the list of file names. We're gonna get the third one, and we're gonna load it, resize it to 150 by 150, and then turn it into an array. We're gonna extend the first dimension for compatibility to have this tensor, a unitary dimension for the batch size. And then we're gonna use the data gen flow. And notice that the image data generator, when you create it here, you have to use a flow method to get the data from the directory. So instead of using flow from the directory, we use flow to get one image. So that's what we're doing here. We get only one image, provide one image, and with the flow method, we're gonna get the actual generator. Well, I guess in here it doesn't return a generator, just it returns the image. So it's gonna take this image, the image that we picked it up, and it's gonna apply the configuration of the data augmentation, the affine transformations into that image. So the batch size is gonna be just one. So we pick up the only image in the batch. So we're gonna plot four figures. Notice here we're using modulo operator, sorry. So when we reach 4 images, we break. So we're only going to plot 4 images. So for each of those images that we get from the data generator, we're going to show it, and we're going to see here that this might be the original image, and this is flipped image. This is a skewed image, I think. So there's a series of transformations that you can see, and these are the affine transformations that the image data generator is using to augment the data. Okay, hopefully that improves the problem of overfitting. Also, dropout. The dropout can be seen as an augmentation strategy. For example, instead of using a fine transformation, for example, if you want to train a neural network to detect noise, one way of augmenting the data is introducing noise, and then train the network to remove that noise. Providing the pristine original image untouched by the noise. So that's a way you can eliminate noise. But a dropout, what dropout is a layer. It's a layer in the architecture of the neural network. And what it's gonna do is that it's gonna randomly set some pixels to blank, to 0, and it's like introducing noise. And that's another technique to handle the problem of overfitting. This is a supervised learning problem, and by introducing the dropout pixels, you still have the same training data. So it's kind of messing up with the neural network to harden it, to train it better. Okay, so we're gonna go to that now. Data augmentation is still heavily intercorrelated, so we also gonna use a dropout to help on this. So we're gonna create another neural network, and it's exactly the same. The only difference is that we put the dropout layer with 50% probability of having a pixel set to 0. Okay, we compile it with the same parameters: binary cross entropy, root mean square propagation, and accuracy as the metric, and use the image data generator, and this time with augmentation, with all the affine transformation configuration. But also we have to scale it this time, scaling of the pixel as we did at the beginning. For the validation, we don't want to apply the affine transformation and the data augmentation because that's for validation. And then once we have the both generators, we're gonna flow them from the directory, provide the training directory, resizing as before, batch size is the same, classification is a binary because we're detecting cats and dogs, and same thing for validation. And then we provide the model with the training generator as we did before, the validation, step for epoch, these parameters are exactly the same, and the epoch. So we run it. And again, we start with a low accuracy, and then the accuracy keeps increasing and it gets farther. And okay, so we're gonna get the history from the feeding. We're gonna save it again. We have the other save file in here, and now we're gonna we just copy pasted these instructions for plotting. And so notice now that the validation data is closer to the training data. So validation data accuracy increased to more than 75%, 76%, which is an improvement. But also notice that how the training accuracy diminished from 98 to less than 75%. So it's like a regularization. The overfitting techniques of augmentation sacrifice accuracy of the training data in order to have better validation data, which is good because we don't want to overfit. We don't want to make this optimal for the training data. We want to make this as general as possible. Okay, so we can keep playing around with the layers, adding additional regularization techniques, and increase this from the scratch training a neural network to 86 or 87%, but that's a lot of work. Notice also that we have 76 accuracy, validation accuracy here, but we are dealing with a couple of problems. First, this is not like the digit training. The digit detecting digits is a very simple problem. The detecting cats and dogs is more complicated. Second, we have only 2,000 photos, so it's a low amount of data. So rather than training a network from the scratch, we're going to use a pre-trained neural network, which should get us better performance, and that's what we're going to do in the next video. Thank you very much.